This is going to be a short video to fill in a couple of questions that are related to computer assignment 2 that we didn't have a chance to go over in class. So the first thing that I'd like to do is talk about the concept of scales of measurement. So we talked about qualitative data, which is basically either data that is non-numerical, or if it is numerical, it has a finite set of numbers, and those numbers don't really refer to numbers. They're more like student IDs or product IDs or things like that. We also talked about quantitative data, which is numerical data. So within these categories is another way to describe the data and in some sense understand subtypes, and that's based on scales. So for qualitative data, we have two kinds of scales. We have what are called nominal qualitative data and ordinal. Nominal is the least sophisticated, and but that doesn't mean it isn't common. It's probably one of the most common. Basically, it's just values that differ by a label or name. And again, here, the key thing is that there's no ranking. So hair color, eye color, student ID, things like that. You wouldn't necessarily consider someone a better student because they had a higher student ID. So that's what we mean by nominal. There's no ranking. The next kind is ordinal. And ordinal is the type of qualitative data or categorical data that, again, is not, it meets the conditions of nominal in that it's either words that describe a quality like eye color or hair color, or a student ID. But the difference is these can be ranked. But the key thing with ordinal and what makes it qualitative data is you cannot interpret the difference between the ranked values with some kind of numeric quantity. So for example, movie reviews, you could have 1 star to 5 stars, but you don't really know what it means what's the difference between a movie that's got 4 stars versus 5 stars. There's no way to give that a number. It's just a as far as like just on the number line. It's the only way to refer to it is by talking about how many stars it got and understanding that 1 star is a lower quality movie than a 5-star movie. Okay, so those are the two types of subclasses, if you will, and really what we're talking about are the scales for qualitative data. And then for quantitative data, we have the interval scale and the ratio scale. By and large, most of your data is going to be in the ratio scale when it's numeric or quantitative. And for that, you need to have a true 0. In other words, whenever you say 0, it really means 0. So if you're talking about income, it means no income, right? If you're talking about height, no height. If you're talking about, I don't know, anything else, it is just that it means something. Let's just say a regular number otherwise. And the reason it's called the ratio scale is because ratios are meaningful. So like profits. So you can take a ratio of one number to another number. And like I said, the vast majority of numerical data is quantitative ratio scaled data. There is a subclass that has an interval scale. And here you have categories and rank and differences are meaningful, so that makes it quantitative. But the 0 value is arbitrary and does not reflect the absence of the characteristic. So the really good one to think about as an example of an interval scaled quantitative data is temperature. 0 does not mean a lack of temperature. You can go below 0. And 0 is a temperature doesn't mean, yeah, like it's not there. That doesn't make any sense. So it's considered an interval. Okay, and that's it for that. The next thing I want to talk about is when you're getting quartiles of data. I'm going to pull up some data now and open up some data just to help us look at something while we're doing this. So let's go to car prices here. So here's some data on the price of a car, the age of the cars, and the miles that the car has. Okay, assume that we wanted to get some, we wanted to find the quartiles on the price. So one thing that we could do, I'll just do it right over here. So I'm going to say Q2 and sorry, not Q2, Q1. Q1 and Q3. So the first and third quartiles. When you do this in Excel, Excel is going to give you some choices. And so if I hit quartile, I get quartile period EXC, and that says it returns a quartile of a data set based on a percentile value from 0 to 1, comma, exclusive. And if I choose the one that says inclusive, it says the same thing, except at the very end, it says inclusive. So what this means is it's going to include the 0th percentile and the 100th percentile when it's in, or the min and the max, if you will, when it's doing its calculations. The quartile period inc for inclusive is the one that most statisticians feel is the appropriate way to calculate these. There are some reasons in some special situations where you'd want to use the other quartile function, but by and large, the one you want to use is this quartile.inc. So if I want to get the first quartile of price, I'm going to put price in here, and then I'm going to put comma, first quartile for the 25th percentile, right? So that gives me that one. And then if I want to do the same thing for the third quartile, I want to again pick a quartile inclusive, put in my data, and I don't have to sort it. I don't have to do any of the hard work of getting the median of the top half. I can just have Excel do all that work for me. So Excel will find those values for me as shown here. Okay, the next concept I want to talk about that you're going to need to know for the computer assignment 2 is when we are talking about the correlation. So in order to do that, I thought that the best thing would be to just go ahead and talk through the textbook on where this is covered. So this is covered, if you want to read it in more detail, in section 14.4 under linear correlation. And you are not going to be responsible for all this material that's in this section. I am just going to cover the concept of linear correlation, and I want you to just have like an introduction to it. So for example, when we talk about linear correlation, I'm going to actually start backwards from where the text is. Hopefully I can kind of get there. All right, this is where I want to start. Basically, the correlation coefficient, which is the R, it's referred to as R, and it's going to be a number that goes from 0 to 1. -1 to +1. When it is +1, let me get my annotation stuff here. When it is +1, we have a perfectly positive linear correlation. That means all the points are going to lie on this line, and the slope of the line is positive. Okay, the r equals 1 tells us nothing about the slope. All it tells us about is how close these points are to landing on this line. Okay, if you have a strong positive linear correlation, here's an example of one that has a 0.9. You have some points that kind of come off the line. And by the way, this is what's called a scatter plot. So every point on this graph, and let me just point to one of them. Any point on this graph is an XY pair. It's hard to draw in here. It's an XY pair. And that means the X value represents one quantity and the Y value another quantity. And they're coming from the same individual item. Like it might actually be a person, it might be a field, but you are looking at two things that are in some way connected. They're coming from the same individual. They're just different things that are being measured. Okay. So when we put a scatter plot and we see that a line can fit the dots perfectly, we have that perfect positive linear correlation of R1. And then as R gets smaller, we start seeing that we have more deviation from that line. So you see a little bit of what is sometimes referred to as noise or variability in the data. But you can see here we have a weak positive linear correlation where R is 0.4. And so we have a cloud of points, but there seems to be a trend up. You could kind of put a line in there to identify that trend, and where exactly you draw that line is a big topic called linear regression, which is a very important topic, but we are not covering it in our class. It is introduced and covered in 211. I recommend you take 211 even if it's not required for your major. But regardless, this is what a weak linear correlation looks like. Now, if we go to a perfect negative correlation, we have an R of -1. And again, the slope is negative. The perfect score of R equals -1, again, is not telling us anything about the magnitude of the slope. It's only indicating that the points are lining up perfectly on a line. And again, as that magnitude is not as great, so R of -0.9, we start seeing variability around that trend line. And then a weak negative, we can see an even greater variability. And these are not the only numbers R can take on. They can take on any number between +1 and -1. In between, we have this case where there's no linear correlation. And this means that they're linearly uncorrelated. So you see a cloud of points. In some sense, you could draw a horizontal line and say that the slope is 0. But if you are able to draw a horizontal line as a trend line through your data, that is associated with an R equals 0 or no correlation. Okay, so now that we've kind of talked about what it means when you have different kinds of correlation, from strong positive, perfect positive, to strong, to even weak positive, and a negative where you have a negative slope on the trend line, and again, perfect, strong, or weak. We see we can now back up actually and see what the formula looks like to give us R. Now again, this formula is not necessary for you to know. It's just really for curiosity's sake. So here is what that formula looks like. So it is 1 over n-1, where n is the number of data points. And R is defined as 1 over n-1 times the sum of each xi minus its mean times yi minus its mean, all of that divided by this product of the sample standard deviations. Okay, so kind of a messy function, but again, we don't need to, we're not going to do a deep dive here into this. What I do think is important though, is that we identify a few things about this. So the R reflects the slope of the scatter plot. And basically this kind of, you can read through this if you want, it has a little bit of a more depth in description of where that comes from. The magnitude of R indicates the strength of the linear relationship. And I just crossed it out there, but it's from -1 to 1. Okay, with a R value near 0 indicates at most a weak linear relationship. Usually it's considered, if it's close to 0 or 0, there is none. The sign of R suggests the type of linear relationship. So again, if it's a positive R, it's a positive linearly correlated. If it's a negative R, it's a negatively linear correlated. The sign of R and the sign of the slope of the regression line are identical. Again, we are not discussing regression lines, but it's a very related topic to this. Okay, and in order to calculate the regression, it's really, the correlation coefficient. I'm going to show you how to do that in Excel, but one thing that's important to understand is that depending on some weird ways that your data could have values, you could get some of these, you could get R values that would imply you have a linear relationship, but if you actually graphed it, you don't. So it's really important that you start, before you do a correlation, that you actually graph your data to be able to decide if you can trust the value R as coming from the scatter plot. In other words, you need to see a trend in the scatter plot before you would trust the R, because mathematically you could have some, like a U-shaped data that could tell you something that you think is there that isn't there. Okay, so let's go ahead and try and find this. So here, going back to our price data, we maybe want to know, is it possible that the price and the age of the car are correlated? Now remember, something important is that correlation does not imply causation. So we don't, from a correlation coefficient, are able to say that one thing causes another. We are just able to say there is this relationship. Okay. So let's say we think that there might be some connection between price and age. The first thing we always want to do is graph it. So I'm going to select this data, go to Insert, and then in the charts, I'm going to go to this one that says Insert a Scatter, XY, or Bubble Chart. And I'm going to choose the scatter. And here we can see that the price, so we might want to give it some axis titles. So this is the price of the car. And over here is the age of the car. Okay. So price versus age correlation. So if you notice, it does appear as if there is a trend in this data. So let's say we wanted to actually get that R value, the correlation. What is the strength of this correlation? In order to do that, we just use this function. Hold on, so let me just identify what I'm doing here. And it's going to be equals CORRR, CORREL, correlation, returns a correlation coefficient. And it's going to say array 1, array 2. So that it just wants the values in the one column. You got to have the exact same number in both of the arrays. If not, you're going to get an error. So in this case, I put these together and I see that I get a correlation coefficient of minus 0.91. So this is very, very strong. This is a strong negative correlation, saying basically as the age of the car goes up, the price comes down. And that certainly corresponds with what we expect. Okay, so that's it for the quick correlation overview.